So we start with Coulomb's law in vector form. So let's look at what is Coulomb's law. Coulomb's law, so far we have studied Coulomb's law in what manner? We have studied only the magnitude part of it, okay? So the electric force between two charged particles is given by 1 by 4 pi epsilon naught. And I'm assuming that the two charges are in free space or in air. So I'm not putting K just to confuse it further. And okay, if you want K, if they're in any other environment, then there will be a K. And then this is multiplied by the magnitude of the two charges divided by the distance of separation between them. Now this gives me the magnitude of the force. And if the signs would have been opposite, the force would be attractive. If the signs are same, then the force will be repulsive. Is this much understood? Now when you talk about, say, Coulomb's law in vector form, then you need to understand that the quantity that you are trying to find out is called force, and force is a vector quantity. That means you should specify both the magnitude of force as well as the direction of force, right? This expression does not tell us anything about the direction of the force. That is what we are supposed to hunt, right? Now a little bit of more groundwork on that. When I talk as the direction of force, then we have already studied that the direction of the force is along the line joining the two charges. So let's say I have a charge which is a charge Q1 and I have a charge which is Q2, and then I should first have a line that joins the two charges. So this is the line that joins the two charges, and my force, okay, my force. So instead of going for force, we should also say let Q1 and Q2 both be, say, positive charges. That's the best way to understand. So I will have a force now. The force will be a repulsive force, and this force is going to act along the line joining the two charges. Do you agree? Right? This is Q1. So I would say the force on 1 due to 2. Now I'm putting a vector sign because I'm also interested in the direction. And the force on this, I would say the force on 2 due to 1. Understood? Our job here is actually to give the direction to this force. That's Coulomb's law in vector form. Now the magnitude part you have already addressed, right? Now before going this, we need to also have our concept where you are getting it difficult, because you need to have the concept of something called position vector. Position vector. How do you define the position of an object in a quadrant? How do you define the position of an object in a quadrant? Now say suppose this is my xy axis and this is my origin, right? This is my x-axis and this is my y-axis, right? So I have a point out here which is a point P. Do you agree? And P, if I try to map it down here, if I try to map P down here, this is the x coordinate of P, so that your vector basic is absolutely clear. All right. Now tell me, children, this is a point P xy. Don't you agree that this should be the point x and this should be the point y? All right. Now this is Cartesian way of representing it. What am I doing? The entire this thing is black from here to here. Paint, charcoal. Okay. So from here to here, this is Pxy. So x from this side. This is Cartesian way. Now we will try to represent it in vector format. So to represent it in vector format, we will have a position vector. This is the position vector. So I call this as my position vector R. And my position vector R is equal to, now what is R? Just try to think. R will be a hypotenuse which will be x square plus y square. So in vector, see, the good thing about vector, which you should have learned in 11 in a nice manner, like 3 plus 4 in algebraic sum is how much? 7. But in vector, a 3 and a 4 will give you how much? 5. You're doing a vector sum. A 3 and a 4 gives you 5. So I write my R as, R is what? X, on X units on the X axis. So on the X axis, what is the unit vector? I. So this will be an I cap plus Y j cap. This is how you understand. R is a point. Looking at this, you can find the Cartesian coordinates also. So this, if this was say by that example, if this was say 4 units and if this was 3 units, then I would say that R as a vector is given by what, children? R as a vector is given by 4i plus 3j, right? And modulus of R will be, since they are maintaining 90 degree, what is the modulus of a vector? A square plus b square plus 2ab cos theta. A square is 16, b square is 9 plus 2ab, whatever it is, 2ab, blah blah, into cos theta. The angle between the two vectors is 90 degrees, so it becomes 0. That's how you get. What is the modulus of R? 11 में किया है मस्ती. So that is equal to 4 square plus 3 square plus 2 into 3 into 4 into cos of 90. That's how you get it. Did you understand? Now this was nowhere related to this, but if you don't understand this, then the other one doesn't become clear to you, right? So let's talk about, before the charges, let's again talk about this is 1 and right. Now first basic vector basics, then we will go to Coulomb's law, then your job will be easy. Okay, now I have 2 points out here, say point P and point Q. Agreed, children? P is represented by a position vector. P is represented by a position vector which is say R, and this is another position vector which is say S. Is this clear? This is position vector R. Means P would be a point. We are doing vector algebra, okay? X1, Y1. Then we can express R as a vector as what? X1i plus Y1j. Similarly, this is a position vector X and this is X2, Y2. So S as a vector can be represented as X2i plus Y2j. Look, they tell you that in x-axis, what is the unit vector? Then x-axis, the unit vector is I, right? Now, we want to find out in vector beta, PQ can be one displacement and similarly QR can also be one displacement. Do you agree or not? Right? So let me clone up this diagram so that your concept becomes easy. So in one diagram we'll show you PQ, in one diagram we'll show you QR. Okay, the first diagram we will try to see what is PQ. Means we would be moving children from P towards Q. Do you agree? In the other diagram we are trying to see, and the other diagram, what you don't want, it will plot that. Okay, in the other diagram you want to see what? QR. So this is QR. This is QR. Are we fine? Okay. So let me call this as PQ vector and let me call this as QR vector. And let's try to, I didn't get you?
Yes, QP.
Oh, QP vector, yeah. Sorry, I am aging. I realize that nowadays. So QP vector, okay. Now apply vector sum means, see, consider them as displacement and go back to grade 9. If you come back to the same point, your displacement is how much? 0. Your displacement is 0. So Zoe, you start from here. How do you start? You take R vector and you are going PQ, means you are still moving along the same side. Heads, tails, honored. So you say this is PQ. And then you suddenly say, S is obstructing you. So you can say minus S vector should be equal to 0. So if you want to separate PQ vector from here, it would be S minus R vector. Or else you start from PQ. PQ, obstruction, minus S. Again, happy. Let's do it from here. So we'll start with, say, S vector out here. S vector plus QP vector minus R vector is equal to 0. So your QP vector becomes equals to R vector minus S vector. Understood, children? Okay. Now, if I make it negative QP, then these becomes negative of R minus negative of S. Do you agree? That means this becomes S vector minus R vector. Do you agree? Can I not write this as PQ vector? So we understand that in vector algebra, PQ is just opposite of QR. Again, QP. I'm sorry. That is, excitement wins over vocabulary sometimes. So PQ is QR. Is it clear now? Actually, these things were not clear with you guys. That's why you used to find that expression and things there. But this has nothing to do with Coulomb's law. This will be used in Coulomb's law. So we are actually spending time now chopping onions, where we have to make actually a biryani. Shall we go back to biryani preparation now? Okay, let's go back to Coulomb's law. So I start my Coulomb's law's illustration in vector form. So I have made a Cartesian coordinate system, and Coulomb's law is all about two charges. So let me put my two charges, one charge here and one charge here. I call this charge as Q1 and I call this charge as Q2, and both the charges are placed at a frame of reference, which is my Cartesian coordinate system. So I should have an origin, and from origin I have mapped the two charges in this manner. Right, or child? And since the force acts between on the line joining the two charges, I have put the line joining the two charges also out here, and both the charge being positive, so they are going to encounter a repulsive force. So this is the first repulsive force, and this is the other repulsive force. Right? Clear? This repulsive force is the force on 2 due to 1, and this repulsive force is the force on 1 due to 2. Righto? No issues. This is my y-axis. This is my y-axis. This is my origin, and this is my x-axis. Position vector to Q1 is given by R1, and position vector to Q2 is given by R2 vector. Are these things clear? Obviously, I'm okay. For you guys, I'll do that. So now we'll clone this up. Now we'll have two sorts of displacement. We'll have two displacements. One displacement would be from Q1 to Q2, and one more displacement will be from Q2 to Q1. Achha, why I have taken two displacement? Because force, whenever we talk about force, force is experienced by the displacement, right? If I push you, how do I know how did I push you? By the way you move. So if you move in that way, that means either you have been pulled that side or you've been pushed from that side. Both means the same, right? So this, we're going to name the two vectors now. Now this vector is from charge Q1 to Q2. So I'm calling this as R12 vector. Agreed? And similarly, I call this as R21 vector. Now job is all easy, right? One thing we have understood, children, that the F21 force is just the opposite of F12 vector. Now understand this diagram. This statement means vector wise they are opposite, magnitude wise they are equal. So whether you study this force or you study this force, from the scalar perspective, it means the same thing, right? Coulomb's law does not tell us this or this. Coulomb's law tells us what is the force between two. So either you are analyzing it from this perspective or this perspective, right? So since we are doing vector form, we have to pick up any one force. So I'm picking up the force F21. F21, right? F21 is a force which is given by 1 by 4 pi epsilon naught. What is the dielectric constant of the medium? Q. K. Charges being scalar will be written as Q1 upon Q2. But now I have to say F21. Which direction is F21 going, children? F21 is going along R2, R12. R12. Because you have to take the force along the displacement. So I write it as R12. Did you understand this? But here we use the magnitudes, square of the magnitude. But since this is a vector, you need to give also a direction to it. What is the direction? The unit vector along this direction. Where a unit vector R is always the vector R stripped off of its magnitude. Remember this. Righto? Clear? So similarly, if I take a force F21, I would write this as 1 upon 4 pi epsilon naught K, K being the dielectric constant between the two mediums, and the scalar product of two charges, and this time it will be an R21 vector square, and you need to give a direction, so it will be R21 cap. Understood? Do you want me to derive again that R21 and R12 are opposite to each other? If you want, you can do that again. Okay. Now you can add some more interesting observation to it. If you bring down this statement, the statement can be written as F21 is equal to 1 upon 4 pi epsilon naught K. Now look here, this is Q1, Q2, right? Break this unit vector. What is a unit vector? A unit vector is the vector which has been stripped off of its magnitude, and you already had one R12 square here already. The square in this becomes cube. That's why in some books you will see it as cube. In fact, that is the right way to write. This is 1 upon 4 pi epsilon naught K Q1 Q2 divided by, I'm going for R12 vector cube into R12 vector. And similarly, in the same lines, this force can be now represented as F12 vector equal to 1 upon 4 pi epsilon naught K Q1 Q2 R21. I'm trying to open up this unit vector. So the unit vector is the vector divided by the magnitude stripped off, and here you already have R21 square. So this becomes 1 by 4 pi epsilon naught K Q1 Q2 R21 square R21 vector. And now you play that wonderful thing which you play between these two, that R12 is negative of R21. This I have already shown in the previous one, PQ and QP, right? So based on this, you can just swap R1 to R. You can say that F R12, so this is F21 is equal to negative of F12. Forces are same, they're just opposite direction. This is Coulomb's law in vector form. So you tried to show, children, see, you tried to show Coulomb's law in vector form by elaborating a whole scenario. And now if you want to generalize it, you are not bothered about what is the force experienced by Q1, what is by Q2. You're only bothered about a force F. So if you want to summarize Coulomb's law in vector form, you would say the force, electric force between two charged bodies given by 1 by 4 pi epsilon naught K. Then you will say a Q1, Q2, and then you will say R as a vector divided by R vectors cube. And if you don't want to write cube, you want to write square, then this becomes unit vector. This can also be written as 1 by 4 pi epsilon naught K Q1, Q2, R vectors square multiplied by R cap, which is the difficult. It's easy. Your concepts were not clear about how R1 became R21, and maybe in your school they just derived it. So you felt that this is some Hebrew Latin being taught to you. Right? The basic is because here in Coulomb's law is not tough part. Tough part is the vector algebra, which children don't want to, or in 11 you have not studied it properly. That's the only thing. Fine? Can I go ahead? So, how much have we done? This is done, this is done. Okay. Okay, our next topic. Our next topic we carry forward from quantization of charge, and we will be coming upon volume, continuous charge distribution. So let's revisit quantization of electric charge. Quantization of electric charge tells you that charge always comes in multiple of n, right? So the net charge, or you can say the total charge magnitude, obviously magnitude because charge is a scalar quantity, is an integral multiple of E. Do you agree? Where E is electrons. We take the charged bodies as always electrons because protons are very loved by their mother nucleus, and the mother nucleus does not allow the protons to go outside and play in the park. So it's only the electrons who play. So electrons are my charged particles, right? Integral multiple. So if I have large charged bodies, okay, large charge containing, I say the English is not right. We say bodies containing enormous amount of charge. Okay, so if I have a body that contains enormous amount of charge, if you have a body that contains enormous amount of charge, it means large number of electrons. Do you agree or not? Right? Now look, children, the LCD panel on which I am writing right now, my stylus is writing on this because there is a charge here also, there is a charge here also. Do you agree? Or you're able to move the screens on your phones, smartphones, because the screen is also charged. That's why when you wear a gloves, you're not able to move it anymore. Now, these bodies are said to be having a continuous charge distribution. Now, what is a continuous charge distribution? Have you greased a butter cake tin before with butter before pouring the batter? So it's a continuous spread of butter. Imagine the cake tin to be so big that it spreads from here to say another apartment out here. So can I say that butter is at one place? No. The butter is the charge out here, and we are studying all about charges at rest. But the charge is such a fellow. So the charge is such a fellow that the charge is actually spread all across, and it's a uniform spread. Now it can be spread over a surface, it can be spread over a thin strand of string, it can be spread over a volume also. studies about charge. But in that time, how do we quantify that amount of charge? How do you know how much butter is spread from here to another apartment when you're greasing that butter thin? So that concept is known as continuous charge distribution. And this is what I hope in your school you must have done a lot of problems on Gauss law, then thin sheet of charge, sphere of charge, which head and tail you must have not understood anything. Okay, so continuous charge distribution. Grasp this concept, it might become a little bit easy. Continuous charge distribution. So in continuous charge distribution, we will not talk about, see, it doesn't make us any sense for, Hyderabad is very populated nowadays. But I would not have any, it doesn't give me any sense to know what is the total population of Hyderabad. If you just tell me what is the population density, and you tell me that the population density of Hyderabad is say we have 400 people per square kilometer, means in 1 kilometer by 1 kilometer square, how many people are inhabiting that place? 400. And I say the same thing to some small town in Australia, and they say 9 people per square kilometer. That density makes it more easy for me to understand that this is a populated city, this is the whole count of the population of either the town in Australia or that in Hyderabad does not make any sense to me, right? So similarly, here also the concept is like this, that the bodies are very big and they have a continuous charge distribution. My study is about charge. So I will now focus my study on something called the charge density. Charge density. And while we study this concept of charge density, we will also like to appreciate what is your body. Now, your body can be a 1D body, your body can be a 2D body, your body can be a 3D body, as simple. When we say 1D, I would say something like, say, a thin wire, no cross section. Are you understanding? No cross section, like the strand of your hair. Can you see the cross section of your hair? No. So it's like it is having almost 1D measurement. Understood? Or it can be a thin wire or a thin ring. These all fall under a category of 1D. If I say 2D, it is like a thin sheet of charge. Sorry, a thin sheet, not of charge, a thin sheet. A thin sheet can be analogous to a 2D. Means it does not have, it does, in a thin sheet is something like a paper. You can move on x-axis, you can move on y-axis, you can calculate the area of that. Agreed? And when you talk about 3D, you know, this can be a 3D sphere. Something like a 3D sphere, which you must have heard a lot in Gauss theorem and all. Which one? Thin ring means take the same wire and make it a ring. You can open it up, right? Now, if you try to appreciate these three, this one is like a line. A line on which charges will be there. Have you seen a thread where manja is spread? It's like that. The manjas are the charges which are spread over a line. This is line. This fellow, in physics we call it as surface, or I would use the word area. Area, spread across the area. And this fellow I will call as volume. I don't think you have any difficulty in understanding this concept, right? So I have now continuous charge distribution over three different types of bodies. A one-dimensional body which is like a thin wire, and there it is the length that matters to me because the body is infinitely long. I can have continuous charge distribution spread across an area or a surface like a thin sheet. I can have continuous charge distribution which is over a 3D surface inside. Got it? So let's could you understand this one? Like say you are adding color to an ice cream and the color is uniformly blend into the entire ball of the vanilla ice cream that you are eating. Not vanilla cannot have color. Say strawberry, yellow. So the yellow color is spread across the volume. Not only outside, inside also. Okay. So let's put our, so whenever we come across these three things, which will come a little bit later, we have something called line charge density. line charge density, and this is denoted by lambda. This is denoted by lambda. What is density? Mass per unit volume. You are studying density of what? You are studying density of charge spread over a length. So charge per unit length. So we will call it what? We will call it as charge per unit length. That is all about length charge density, line charge density. So this is given by lambda, which is given as del Q over del L. Now, do you know the difference of this d, small d? Little bit of calculus. Okay, please understand. Suppose you have something called this is called delta Q over delta L. This is called del or dq. This is a smaller fellow. If this fellow is given a limit where we say delta L tends to 0, means the small length that you could conceptualize, it is even smaller than that it is approximately approaching 0. At that time, this quantity, this whole quantity is expressed as dq by dl. So it is ekdam chota beta. Understood? Little bit of concept on this from say grade 11. Average velocity is the change in velocity per unit time, delta v by delta t. If you now try to put a limit to average velocity and you say that you are bringing delta t to 0, that is, you put a limit with delta t to 0. Now you try to appreciate this, then you'll understand. Delta v means there are two time instances where there were two velocities. You found the difference over the time difference. Now you are saying that the time difference is very small. I saw Zoe today. I saw Zoe yesterday. The time difference is how much? 24 hours. But you are saying, please reduce your time difference. How much can I reduce as a human being? The blink of an eye? That's the time difference. I call it dv by dt, which is instantaneous velocity on which the traffic cop ticketed you. On that particular time, what was the speed? Did you get it? I saw her over a period of 24 hours. You said, no, reduce the period. Bring it almost to 0. How much can I bring it to 0? One blink of an eye? That's my instantaneous vision of her. That is called instantaneous velocity. And that is what you find in a car. So this is a little bit of calculus. So you come back here. This is what dq by dt. This is called charge per unit length. So we'll have this. Then we will have one more, which is known as surface or area charge density. Area charge density. Now you might ask, sir, what is the use of studying all these? These will be used based on the type of cases you interact. If you have a thin wire which is infinitely long, then you cannot know what is the total charge on that body. And doesn't make sense to you also. What is the population of Hyderabad? You would like to know what is the density of Hyderabad. You'd like to know what is the density. And now bring that concept. Every time we won't give you only what is called a thin wire. We might give you a sheet also. At that time, surface charge density comes up, denoted by sigma, which is given by dq over dA. dq over dA. Got it? And the third one will be known as volume charge density. And the volume charge density is represented by rho. Rho is the very good density symbol that we know, mass per unit volume. So it will be given by dq over dV. So this is charge per unit length. This is charge per unit area. And this is charge per unit volume. Children, we are all set to enter the new topic of electric field. But we will now get into numericals. After that only we will get to electric field. Tell me, Hebrew, Latin, or you understood something? Very good. Very good. Noted? Okay, right, fine. So let's go with some easy questions. After many years, I dug out these notes. Yeah, some 4 or 5 years back. Okay, let's do some problems. You can write the question as I'm dictating, but I'll write the salient things. What is the force? What is the force between two small charged spheres having charges 2 into 10 to the power minus 7 coulomb and 3 into 10 to the power minus 7 coulomb placed 30 centimeter apart. Is the question complete here? No. What is missing? What is missing in this question? What am I asking to find you? What did I ask to find out? Force. Force is charge values are given, distance of vibration is given, question is incomplete. What is missing? What is missing? Charge spheres, small charge spheres are like two beads of your necklace. What is missing? You can't solve this problem. K. The medium is missing. Yeah. Apart in air. Unless this is specified, how will you understand whether it is 1 by 4? So in air means, children, in air means you can straight away apply the small k, which is given by 1 by 4 pi epsilon naught. And otherwise you have to apply 1 by 4 pi epsilon naught, and you need to put a big K where big K's value is equal to 1 for air. Now do it. And do it in proper manner. Given Q1 is what? Q2 is what? It's your problem solving skill. Yeah. Okay, if you have just, I'll allow you to do both the problems. Just give me 1 minute of yours, please. Very sorry to stop in between. Some conversions which you should be very much familiar with. Okay. So it's, know this thing, exa, eta, tera. This should be in capital actually. hexa, beta, tera, giga, mega, kilo, hecto, deca, deci, milli, micro, nano, pico, femto, atto. Right. This is a conversion that you should know. This is 10 to the power 18, 10 to the power 15, 10 to the power 12. I have got a hard disk which is 1 terabyte. 10 to the power 9, 10 to the power 6, 10 to the power 3, 10 to the power 2, 10 to the power 1. And here will come whatever is your quantity, meter, liter, gram, whatever. Deci, 10 to the power minus 1, milli, deci, sorry, I missed out one. That is centi. Centi is missed out. So here we should have centi, which is 10 to the power minus 2, 10 to the power minus 3, 10 to the power minus 6, nano, 10 to the power minus 9, pico, you will attack a lot in capacitance, minus 10 to the power minus 15, 10 to the power minus 18. And also we use one more called angstrom. Angstrom is 10 to the power minus 10. Hexa, peta, tera, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, pico, femto, atto. No, you should not memorize. These things you will need. Like when you do capacitance, you will get megafarad, you will get micro, you will get nano, you will get pico also. So this will be written as picofarad, this will be written as nanofarad, microfarad, and this will be written as megafarad. These you should know, these conversions, because if you look at the problem that I gave you now, it has got microcoulomb. Microcoulomb means 10 to the power minus 6. Picocoulomb means 10 to the power minus 12. Yo, what is the answer of the first one? Hey, don't give me all this 1 by and 2 by. Yes, 6 into 10 to the power minus 3 is the correct answer. What are you seeing in the behind? क्या देखना पड़ रहा है इस problem में? What formula? You didn't forget. That means you didn't study from the last class to this class. As simple as that. Force formula is K Q1 Q2 by R square. K is 9 into 10 to the power 9. How am I remembering? ये करने से नहीं होगा. Our last class happened on Friday where I told that please study this part and come. If you study in my house only, the result will not come. Please take that for granted. I will be able to do only 4 or 5 problems. And you don't need, once it is air, the problem is very easy. It's 9 into 10 to the power 9. Even that is not striking you. And this chapter has been done in your school. That means you have not done a single problem from school, and you have not done a, means we are doing problems today, you didn't revise mine. I don't know if there is a third tuition now where you will go and again you will learn this. So this is lost. 12 into 10 to the power 5 what? What? My head or your head? In meters, it will be 12 into 10 to the power minus 2. Why are you getting so much of errors? They're straight numbers. Yes, then I think you all are not efficient in doing calculations with exponents. Let's see what was so tough out here. Where is it? Yeah. So we have to find R in this case, right? So how much is our force? 0.2 Newton, which should be equal to 9 into 10 to the power 9 K. What is Q1, bacha? Where is Q1? 0.4. So it's 0.4 into 10 to the power minus 6. And then 0.8 into 10 to the power minus 6. Agreed? And then divided by R square. That's it. What happened? So if you take R square out now, let's make them some handsome numbers. 9 into 10 to the power 9. This becomes 4 into 10 to the power minus 7 now, right? Because you're making it even more smaller. And then this becomes 8 into 10 to the power minus 7 divided by 0.2 can be written as 2 into 10 to the power minus 1. Agreed? Let's handle all the tens. 9 minus 7 minus 7, and this is minus of minus 1, which will become plus 1. Fair enough? 2 times is 4, right? Then this is 8 into 9 is 72. 72 multiplied by 2 gives me 144, whose square root will be 12. You got it? So let's handle this. 10. 7 and 7 is 14. 9 and 1 is 10. 14 and 10 gone means 4. Not minus 4. Plus 4. Or minus 4. Minus 4. Sorry. This is minus 4. Agreed? And this is 144. If you are still having doubt with roots, let's go back to grade 10, grade 8, then it is something like this. Baby steps. So R is equal to root of this whole thing, which is 12 and 10 to the power 2, which is 12 into 10 to the power minus 2 meters. No, I'm not worried about the answer. I'm saying what appears something clumsy can be made very easy. And this thing will improve in this chapter if you do more numericals. How you are handling. There was a second question also which says, what is the force on the second sphere due to the first? Negative 0.2. If the force on the first is 0.2, then the force on the next. So you can rather than writing negative, you say the force on the second sphere is an attractive force, because one of the forces, negative positive doesn't make a sense. One of the force is positive, or one of the charge is positive, one is negative. So it would be an attractive force of 0.2 Newton. Clear? Shall we take one more? Let's go. Okay, our next question. So we have got 2 point charges now. CBSE will not give you a question which will have difficult calculation. We have got 2 point charges. QA is given as 3 microcoulomb, and similarly you have QB, which is equal to negative 3 microcoulomb. Now this is like a dipole. 2 equal and opposite charges separated by a finite distance constitute a dipole, which we have not yet studied, but we will study. And their separation is 20 centimeters in vacuum. Vacuum means, children, you can happily use small k. Okay. Now, okay, I'll not give you the electric field part. You solve this one. Now, if a negative test charge, you know what is a test charge? A test charge is a very small charge. Okay, we'll discuss about it more when we do electric field. Negative test charge, and the magnitude is 1.5 into 10 to the power minus 9 coulomb. This is the magnitude of the charge. Is placed at the midpoint So AB is a line which actually joins these two charges. If the negative test charge of magnitude blah blah is placed at the midpoint of line AB, what is the force experienced by the charge? Children, very interesting question. First of all, try to understand what it says. And pictures are very important. What happens? We have got two charges out here. We have got two charges. So let me say that I have a distance of separation and I have got two charges. One charge is, this is A and this is B. This is QA. QA's value is how much? 3 microcoulomb. QB's value is how much? Negative 3 microcoulomb, right? And there is a midpoint. The midpoint is O, and at midpoint you have brought another interesting charge, which is Q naught. You have brought a Q naught, and Q naught is negative how much? 1.5 10 to the power minus 9. Negative test charge. That means this is, if you write it in terms of coulomb, what will you write? Nanocoulomb. This is nanocoulomb. You brought this charge. What is the force experienced by this charge? How will you do it? What idea will you use? You have studied that idea. Tell me, last class you have studied. I think we did. Did I teach you superposition? No. Oh, last class we didn't do superposition. Okay, this is, sorry, I missed that topic. We should have thought it. But anyway, this is you. You are experiencing a force due to this and this. So you calculate, no, you will calculate both the forces first and then you will see. Now let's put some idea. This is 3 microcoulomb positive and this is 3 microcoulomb negative. So definitely there will be some force of attraction which will be actually in this direction. Attractive force, agreed? And due to these two forces, it won't be zero, Zoe. Because these two forces, you will face a force of repulsion, negative, negative. And another equal force of repulsion means another equal force. So if whatever is this force, twice of that force you will be feeling. See why she said zero? It appears because this side I have got plus, this side I have got minus. But you should understand like this. Look, Zoe, I'll give it nicely. This is me. I am that Q naught charge. You pull me with a plus. You pull me with a plus, it is zero. But here you are pulling me with a plus and you are pushing me with a negative. The net force is on this side. Agar yehi question somebody gives you an MCQ, na 90% will mark at zero. Because that's the first thought, but it's not zero. Can you calculate now? First calculate the system with 0A. Whatever will be the charge here, you need not calculate this. Because this will be the same force. Magnitude will come this side. After this, just in 1 minute, let's do superposition theorem. That's based on, this problem was based on that only. Will you be able to do this on your own? So we will first calculate, well, if you want to do it in proper manner, then how will you do it? You will first calculate what is the force on Q0 due to QA. And this force will be what? This force will be attractive. And since the force is going on the negative side, you will assume it to be negative. Let's assume it to be negative. Attractive means negative, because it is moving on the left hand side. Agreed? Then you take what is the force on Q naught due to QB. this force will be repulsive, and both these magnitudes will be same, repulsive. So this is also negative, assumed as per on LHS. So the net force will be the sum of these two towards, you don't write finally negative, you can write the net force will be blah 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 to blah blah towards A, to blah blah away from A on the left hand side. Clear? Shall we take superposition theorem? It takes 1 minute. Superposition theorem is not something great. Achha, what did Coulomb's law tell us, children? Coulomb's law told us that you had a two charge system, 2-point charge system. Say suppose you have a charge Q1, which is say positive. You have a charge Q2, which is negative. You have Q3, which is positive. You have Q4, which is negative. You have Q5, which is also negative. You have a Q6, which is positive, right? Now this is called a system of charges. So many systems of charges, right? And your test charge is somewhere here, Q0. I want to find out what is the net charge on Q0. Very simple thing. I have got some brothers who take away money from me, and I have got some granny and grandmas who give money to me. End of the day, I am interested to find what is my net balance sheet. I have more money or less money. One thing that we studied was that whether it is my brothers or whether it is my grandma, I always have a direct relationship between each of us, which is known as the line joining the two charges. Do you agree? So, line joining the two charges. And my test charge Q0, test charges are always positive, huh, children, by default. Test charges have very less value and they are always positive. So what we will do, we'll break the system into 2-point charges system individually, right? So let's start, okay? And I'm not using arrow, otherwise it will get a long time. So let's say between Q0 and Q3, right? My net force will be in this direction. This is F on Q0 due to Q3. It is on this direction. Do you agree? Right? And let's say this is a vector quantity. These are all vector quantities. This is a vector. Now let's say Q0 and Q6. Again, I will have, this will be, I've done it something wrong. Yeah, Q0 is, this is wrong. Okay. Nobody, all of you are sleeping. This force will be on this direction. It will repel, right? F on Q0 due to Q3. Q3 is positive, so it's repelling on this side. This is a vector force. Similarly, if you want to see it with Q6, what will happen? Again, it will repel. This is F on Q0 due to Q6 along this direction. Clear? Then let's look at Q1. Due to Q1, this will again repel. This will be F Q0 due to Q1. Fine, children. Then let's look for Q4. Due to Q4, it will actually come on which side? It will get attracted towards Q4. This is F Q0 due to Q4. This is what you did the problem right now. So we are done with this. Now we are left with Q5. For Q5, our force will be on this side. F Q0 due to Q5. Attractive force. Understood? And then we have due to Q2. Due to Q2, it will come on this side. So F Q0 due to Q2. Now let's see how many attractive forces we have. Okay, how many attractive forces we have. Now this is an attractive force. This is an attractive force. This is an attractive force. Yeah, we have got 3 forces where it will move towards this side. So finally, our system can now be thought like this. Our system, our Q0 is now experiencing forces in this manner. See, Q0 has a force on, okay, Q0 has a force on this side, which is F Q0 Q6. Then Q naught has a force on this side, Q naught has a force on this side, Q naught has a force on this side, Q naught has another force here, and Q naught has another force here. Fine, which is FQ naught Q2, and this is FQ naught Q1, and this is FQ naught Q4, and this is FQ naught Q5. That's it. FQ naught Q3. Clear, children? So if you want to find out the net force, F net, superposition principle says the net force acting on a charge, when placed in a system of charges is the vector sum of the individual force of attraction, each charge taken one at a time. So this will be, if you see them as 1, 2, 3, 4, 5, 6, so I'm writing this as F01, okay, plus F02 plus F03 plus F04 plus F05 plus F06. You will do the vector sum. Vector sum means you have understood what will be the net resultant. Acha, how do we do vector sum? Though not in your syllabus, but you have studied this in grade 11. Vector sum means we will actually make two coordinates out here. One will be the x coordinate and one will be the y coordinate, like this, x and y. And then you will take components of all forces. This will be F06 cos theta, F03 sin theta. Then you equate what are the forces on the x-axis, what are the forces on the y-axis. Finally you will get there will be finally your forces will come like this. You will get some Fx net and you will get one Fy net. Finally, it can be up or it can be down. And then if you want to find out what is the vector sum, that is F net. And this F net magnitude will be given by Fx square plus Fy square. You don't get so many complicated system. You did get one system which was this problem. This was also superposition. You calculated due to each and then you found out what is the net. Since they were on the same axis, so you straight away added. Otherwise, the superposition principle tells us net force on a charge placed in a system of charges is found by the vector addition of individual forces experienced by the charge, test charge, taken each charge of the system one at a time. Or you can make your own sentence also. It means very simple. If you have so many, just imagine that so many people are pulling you up. How do you find out what is the net pull? So you will see what is the net pull of each and then you'll add them. Your problem was simple because you had it in one axis. It can be spread across. At that time, we'll find what is the total of x, what is the total of y. Some y's may be in this direction, some this. So finally, we'll get a y and x. Okay? So practice some, because you get more problems. Not only, you'll not just get electrostatic force, you'll get a field and force together. So next class onwards, we'll start field. So you'll get field problems also along with it.